One of the ways that we learned about this year about preparation of alkenes is the elimination from an alcohol and the elimination from a haloalkane, particularly chloroalkanes. And I'm going to go through both of those with you today. It also introduces us to a thing called Saytzeff's rule, which is Markov-Markov's rule in reverse, basically. So we've got a thing called Saytzeff's rule. So if we have a look at this, what we've just discussed off video, as it were, is that this is dehydration. You're removing a water molecule. And we've discussed that a good molecule for doing that, or a good chemical for doing that, would be concentrated H2SO4. So not just any old sulfuric acid, so not dilute, has to be concentrated. And there's two possible places it could remove water from. And we'll do these in two different colours to show you the two possible products. It could remove water here. So the one that I draw in red will have that removed. Okay, so hence the word elimination. Or it could be removed from here. And both of these are going to give slightly different products, and this is why we need to know about that. So the one I do in red first will have CH3, CH, because that's gone. Therefore, this must be a double bond. CH again, because this is gone, and then CH3. There will be cis and trans isomers of these as well, but I'm not going to show the cis-trans isomerism. Okay, so CH3, CH, CH, CH3. And there'll be cis and trans of those. So that's the removal from the what we call the number 2 carbon, or the number 3 if you count the other way, sorry. 1, 2, 3, because the alcohol's the functional group. So that's removal of the hydrogen from the number 3 carbon. Okay. Or it could be removed from the terminal, or number 1 carbon, to give us CH3, CH2, because this stays now, CH, because this is gone, so there's a double bond here, and CH2. This one doesn't have cis-trans isomerism because there's 2 hydrogens on carbon number 1, so therefore there's no possibility for cis-trans. They are the same atom or functional group, so therefore cis-trans isomerism is not possible, even though it's a double bond. Now, when we did Markov-Markov's rule last year, we added water, normally dilute sulfuric acid actually, or phosphoric acid, to an alkene to make an alcohol. We talked about Markov-Markov's rule saying the poor get poorer, or the rich get richer. This is the inverse of that, the poor get poorer. So what we're looking for is which of the carbons, 1 or 3, because they're the ones where elimination of hydrogen can happen, which of these carbons starts off poorer? Which one is poorer to start with? 3. So this carbon is described as poorer. It has fewer hydrogens bound to it. Okay, and we're comparing it to the other one where the double bond could be made. So the poor get poorer implies this is the most common place for the double bond to form. And we can see I circled that one with red. So that suggests to us that this is our major product. And 50% will be cis and 50% will be trans, by the way, of those major products. Okay, so we end up with a major product. And you don't need to remember Saytzeff's rule, okay, as Saytzeff's rule. You just need to know, you need to be able to describe it. The probability of the double bond forming here is greater because this carbon here, the carbon number 3, has fewer hydrogens than carbon number 1. It always has to be carbon number 2. Why does it always have to be carbon number 2 as one of them? What's on carbon number 2? OH. It's got the OH from water, so it's got to be removed. So therefore you're looking at the 2 neighbouring carbons to number 2, 1 and 3. So therefore, what if this is the major product, what do we call the 1-butene which has been made here?
Minor product.
Minor. Cool. So it's all the same as Markov-Markov's rule. So much so that we don't normally give Saytzeff any credit, because all he did is took Markov-Markov's rule and checked to see if it worked in reverse. And it did. So he didn't quite get the credit that Markov-Markov got. Fairly or otherwise is up to you to decide. I'm going to take someone else's idea and see if it works in reverse. Don't know that he deserved a lot of attention on it. Okay, so that's one type of elimination. The other type of elimination is when we start with a halo alkane. So all I'm going to do here is do exactly the same molecule, but instead of it being butane 2-ol, it'll be 2-chlorobutane. So I'm going to start with 2-chlorobutane. I'm not going to break it up as much as this. I'm going to do it shorter. All right. So I'm going to have CH3, CH2, CH, I am put Cl down there though, just to make life easy, CH3. So in this case, rather than being dehydration, when I eliminate, it's going to be Cl and an H from one of these two carbons. So what's H and Cl making? What's that called? HCl. Hydrochloric acid or hydrogen chloride. So, bless you. So concentrated sulfuric acid as a dehydrating agent removes H2O from things. What do you think would remove an acid out of something? Sorry? Not another acid. Nice idea, I like the thinking, but not quite. What gets rid of acids? A base. Okay, let's put a base in there. We could use sodium hydroxide or potassium hydroxide. Both are equally as good. Okay? The problem is, if they're aqueous, dissolved in water, there's such an excess of hydroxide ions, you don't get elimination, but you get substitution. So the OH goes in place of that. So it rips the Cl off to make KCl or NaCl, and the OH goes in making that alcohol. So you've achieved nothing. So instead what we do is we dissolve it normally in ethanol, first of all, because then you don't have the OH ions in solution to do the substitution. You have the KOH in there able to rip the HCl out, basically, to neutralise it. So we write in here ALC in brackets, which is possibly a subscript you haven't seen before. It means it's dissolved in alcohol. That's all it means. And again, it rips it out, so it rips the chlorine out and one of those hydrogens. Just like with dehydration, this elimination reaction has two products, a major and a minor, and I'm not going to write them again because it's exactly the same in this case. Okay, so I'm just going to continue my arrow up. That makes those things as well. So there's two ways to prepare alkenes from other organic chemicals that we can commonly get our hands on. From alcohols or from haloalkanes, particularly the chloroalkanes. The trick for you is remembering that if there are two possible products, you need to know which is the major and which is the minor and explain why. Saytzeff's rule isn't enough, you need to describe it. Carbon number 3 has fewer hydrogens bound to it, so it is more likely the double bond will form there. That's our phrase. Same phrase here. You also need to remember this little thing, the ALC, because it doesn't work with the solid, and it definitely doesn't work with the aqueous. It has to be dissolved in something, so we dissolve it in an alcohol to make this work. Alright? Those are the two things, and that's the new stuff to do with preparation of alkenes from other chemicals. So showing that link between alkenes, and in this case alcohols and haloalkanes. Any questions before I turn that off?